Well, hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomous seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we will have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is my good friend, John Leonard. Dr. Leonard is the Samuel C. Collins Professor of Mechanical and Ocean Engineering in the MIT Department of Mechanical Engineering. He is also a member of the MIT Computer Science and Artificial Intelligence Laboratory. His research addresses the problems of navigation and mapping for autonomous mobile robots. He holds the degree of BSEE in Electrical Engineering and Science from the University of Pennsylvania and Doctor of Philosophy and Engineering Science from the University of Oxford. John is an IEEE Fellow and an AAAS Fellow. Professor Leonard is also a technical advisor at Toyota Research Institute. John's talk today is entitled The Past, Present, and Future of SLAM. Given that it's the beginning of March Madness, I guess that makes this a slam dunk. John, welcome. We're looking forward to your talk.
Well, thank you, Ken. That's wonderful. It's so great to see you. So I'm going to share my screen here and pull up my display. Can everyone see my display? And so I have, it's such a great pleasure to talk to you. I feel like I have such good friends at Hopkins, and I'm really almost ashamed that I haven't visited in person in a very, very long time. Even though I decided to focus on SLAM when I sent in my abstract for the talk, so simultaneous localization and mapping, which has been a focus in our career, I decided to put in a rather long introduction that kind of gives some of the context for how I think about robot autonomous vehicles, and in particular because the notion of assured autonomy really speaks to my heart. I think how do we create sort of trustworthy systems? So the outline of my talk, I'm going to review some of the history and challenges of mobile robot navigation, and then give a little glimpse into our current research in my group at MIT, and close with some discussion of future challenges, open questions. But before that, I want to give a sort of personal introduction. I feel that I won the lottery in life. I'm so fortunate to the things that I've done, the robots and people, most importantly, the people that I've worked with. And I'm going to give a kind of like a sort of a story about my journey in some ways. And so I think about the journey of an autonomous vehicle. Ideally, I'd like to create long-lived autonomous systems that can operate with minimal human intervention and improve their performance over time. And knowing one's position and being able to kind of build up a memory of what you see in the world is a big part of that. And so I started as a grad student in Oxford from 87 to 90. I was fortunate to be in the robotics research group at Oxford, got some of the first Sun workstations in England. The box next to me in this picture is something called a data cube, which was a early vision processing system that cost about $100,000 and at the time could barely do sort of edge detection at 3 frames a second. Computer vision was very much in its infancy, but we used ultrasonic sonars as a sort of surrogate, as a way to sort of try to think about the navigation problem. And so I didn't spend all my time in the lab at Oxford, although it's pretty challenging, like it's a 3-year PhD program. But I did, I pulled out this picture because I have a truly dear friend at Hopkins who I've not seen in so long from my college, Jesus College. Tilak Ratnanathar is a huge Welsh rugby fan, and I threw in a picture of the college rugby team, and we were the Welsh College, Jesus College. And Tilak has had a really incredibly successful career at Hopkins, and he's won a number of awards, and I'm just really proud of his advocacy for the deaf and for bringing technology to help improve people's lives. And so I promise to visit soon, Tilak and Lewis and Jim and all my other Ken, all my good friends at Hopkins. But I came to MIT in 1991, so I'm going to go back to the Oxford part of the story in a little bit in terms of talking about SLAM. But if you know MIT, that I have truly found paradise, you might be laughing. To me, it's one of the amazing things about MIT is the interdisciplinary culture and the ability to sort of work across boundaries in different areas. And I was just truly fortunate to join the MIT Sea Grant AUV lab in its early days. For 5 years, Jim Bellingham was my boss, and probably the best boss I ever had. Taught me so much about the ocean, and we got to do a lot of cool things. We built, the Odyssey vehicle, sort of Jim's vision, and helped program it. Helped with some of the navigation. We have done enough oceanographic operations to just understand how hard it is and the sort of the terrifying feeling of sending a vehicle in the water and waiting for it to come back. From Jim, I learned, the sort of the challenges of AUV technology development. And I think this was the list we had 30 years ago. And I would claim pretty much the similar list today, power, communication, sensing, navigation, autonomy, coordination. In my research group at MIT, we tend to try to focus on navigation as a central capability and associated with that sensing, and then also some projects related to coordination of multiple vehicles, and with colleagues such as Mike Benjamin and former postdocs such as Paul Newman and various Office of Naval Research projects over the years, for which I'm truly grateful for their support, to think about autonomy for problems like mine neutralization and cooperative mapping. And and so been involved with many AUV experiments over the years. I admire my Woods Hole colleagues like Dana Yerger, people that they probably go to sea as many times in a 2-year span than I have in my entire career. We have this wonderful partnership with Woods Hole and through the MIT Woods Hole Joint Program. But some of the vehicles we've been involved with, various versions of Remus and ship hull inspection and Odyssey, and we've made autonomous kayaks to explore cooperative navigation. But I don't, we call our group the Marine Robotics Group, but I actually do a lot of non-marine work. And along the way, about 15 years ago, got involved in the DARPA Urban Challenge. So I was very fortunate to be the team leader for MIT with amazing colleagues, Jonathan Howe, Seth Teller, Amelia Fazoli. And to make a very long story short, we came in 4th place, but it was a sort of almost sort of life-changing experience. And one of the key things about the DARPA Urban Challenge, trying to go 60 miles autonomously in traffic, was they had remote, they had cars following the vehicles with an emergency stop, but the vehicles were truly kind of on their own in terms of if something went wrong, and things tended to go wrong. I tempted to play the MIT Cornell collision video, but I might sort of save that for the end if there's time and go back to it. But if I think back about sort of the DARPA challenge, it really was a pivotal moment for like this birth of this industry, and the sort of story that I'm sure you all know, that Google hired the top technical leaders from the Carnegie Mellon and the Stanford teams, folks like Chris Urmson, Mike Montemerlo, and the Google Car project came along a few years afterwards. And even today, like if I look back at the pictures of the people, folks like Karl Agnema is the CEO of Motional, the Hyundai self-driving startup. Amelia Fazoli helped founded that company. Some of the folks in this picture, like Ed Olson, who's done a lot of SLAM work. Ed has his own startup called May Mobility. Next to Ed, this guy Yoshi, our postdoc for motion planning. He's one of the engineers who landed the rockets back on the barge and on Earth for Elon Musk and at SpaceX. And so it's kind of that human legacy of people, which is really the most sort of the biggest gift, of as we all have working in academia. And just a little more part of intro, my Toyota part of the story, which I figured I should at least mention. I'm fortunate that, back in January 2016, I was one of the first 6 staff on Toyota Research Institute. I went on leave from MIT for a couple of years. TRI grew very rapidly. This is a picture from our all hands in fall 2018, along with Ryan Eustace, who I've worked incredibly closely with at TRI. We talk almost daily. Ryan was a postdoc for Lewis at Johns Hopkins, next to him, Gil Pratt. And I don't know if Ken is in this picture. I tried to find him, but I couldn't find him. And just briefly about Toyota Research Institute, we, looking back over the past 6 years, we had a hypothesis that you could create a single autonomous driving stack that embraced both an active safety application, which we call Guardian, and a full self-driving sort of level 4 application we call Chauffeur. And the sort of our conjecture was that a lot of the shared autonomy functions in perception, path planning, decision making, they could be shared with a system that would sort of protect a human driver as well as apply in a fully autonomous driving mode. And just to sort of a quick highlight, because I think the whole question of how do humans interact with autonomous systems is vital to this question of assured autonomy and trust. And I do believe if you look at autonomous robotics today, look for the human. There are even a system that may seem to be fully have no people on board, like say the Waymo self-driving cars. They do have remote operators. Same with Cruise in San Francisco. And what's a little bit unknown is how much do the human operators step in to take over when things might be not quite right. And so I'm going to give you like a little history. 2017, we did a demonstration in Texas on a private track for Toyota. We created a vehicle with 2 steering wheels. Now, I know Jim Bellingham's an aviation pilot, and dual cockpits are common in aviation, not really common in vehicles. Why would you do that with a self-driving car? Well, what we wanted to do was create a system where we could test having a system that could take over for a human driver, and while still having a safety driver in the sort of left-hand cockpit to take over if the autonomy isn't quite right. And so I'm going to play a little video snippet from something we did back in 2017. So this is 4.5 years ago. And you'll see Ryan Eustace, former Hopkins postdoc, in the driver's seat. Gil Pratt will be narrating. And this gives sort of some of the notion of what a Guardian concept which would be. And our dream is to build an uncrashable car, a car where the autonomy system would prevent the human operator from don't hit things, stay on the road, don't get hit. So let me just try to play this. And
now we're going to demonstrate our Guardian system. We're going to emulate what happens when a driver falls asleep. Guardian can tell by using a camera that's part of the dashboard. The camera can even see through sunglasses in order to see what the driver's eyes are doing, or if their head is moving into a position that indicates they're not paying attention. So Ryan, whenever you're ready, why don't you go ahead and pretend to fall asleep. And now Guardian has stepped in. It's driving the car for you. And now it will offer at some point to give it back to you. Why don't you go ahead and take it now? One of the most frightening things that can happen on the highway is when a car in front of you switches lanes to avoid debris. You have very little time to react because your view is blocked by the car in front of you. We have sensors that can see significantly better than a human driver can see. The Guardian is going to take over where a car switches lanes in front of us in order to avoid debris. Here, that car switches lanes, Guardian decides we have to switch lanes also, and we avoid having a crash. Now Guardian has offered to hand back control, and Ryan has taken control back of the car. So today you've seen demonstrations of 2 basic technologies that the Toyota Research Institute is doing research on. This is all part of TRI's work to eventually build a car that can never be responsible for a crash, regardless of what the driver does.
so partly it seems like just yesterday, it seems like a long time ago. Since then, but the goal was to have the same software apply also in this, what we call a chauffeur application. And so this is something we haven't talked too much about, and really it's COVID. We were working towards the 2020 Olympics in Japan to do self-driving demonstrations in Tokyo, and we everything was delayed, of course, but then the actual, when the Olympics were closed to foreign visitors and media, we basically had to sort of, didn't get really the chance to show the chauffeur system that Toyota developed with partners in Japan. But we developed a fleet of autonomous vehicles and for a neighborhood in Japan with a pretty challenging situation where it's near a port in a place called Odaiba in Tokyo with lots of trucks parked on the side of the road, buses, different kind of pedestrian interactions, traffic rules. And so, we've shown publicly just a tiny little snippet of the system running in Odaiba, and just published a very short summary article in a Toyota technical journal that just gives like the tiniest little flavor of years of incredibly hard work. And so, and I think that clearly there are many companies with kind of L4 chauffeur type capabilities, with say Waymo and Cruise and Zoox at the very lead. And it's clearly an industry that's got tremendous potential for sort of like, robotaxis. At TRI, our goal is to try to really figure out what's the next horizon. So other parts of Toyota, there's a new company called Woven that's been formed, are working on sort of the commercialization of both the Guardian type application for ADAS and the full autonomy. At TRI, I've just recently, I'm actually been on academic sabbatical this year from teaching at MIT, and so I'm helping TRI with a new human-centered AI division where we have some more research that keeps the human in the loop. And we did a press release last month for a project we have in collaboration with Stanford for autonomous drifting, incorporating obstacle avoidance. And so I wish I had time to tell more about this, but this is a time-lapse photo coming out into a small paper we're writing. And this work with led by Avinash Balachandran and Jonathan Go, of trying to basically having a nonlinear model predictive control algorithm that can incorporate obstacle positions. And part of the goal here is to figure out how you achieve performance at the extreme, at the limits of human performance. Again, with sort of the aviation analogy of this sort of performance envelope. The performance envelope of an expert human driver is much better than a typical driver. How do you get the capabilities of an expert driver into a typical human driver, say an elderly driver, a teenage driver, and could that sort of almost like have like a expert race car driver turn on in your active safety system if something's not going right? So that's my very long introduction, and you can see I've been involved with many different types of autonomous systems, but to me it's always been about mobile robot navigation, and in fact. I have a book, it's right there in my backpack. I won't step away to grab it, but just last year I saw the book, How to Get Your PhD, a handbook for the journey. It's just a little handbook, and it's probably full of things that you might say is kind of obvious. But I sort of encourage my students to read it and think about the notion of a PhD as a journey. So a lot of times when I give talks, I try to think about PhD students as the audience, and I feel really fortunate the journey that I've had. And one of the things this book talks about is, how do you find like those key papers that really define like your contribution? There's so much literature out there today with arXiv and all the papers that are appearing. But if you could roll back the clock to 1987 when I started, I was fortunate that the field of robotics was in such infancy. I think about like this inner circle of like this sort of 5 to 10 papers that really greatly influenced me. And I'm going to just talk about a few examples. To me, if we were in a room and it was interactive, this would be where I would like show you a picture and say, hey, do you know who this person is? And raise your hand. We could maybe do it in the chat, but pretend we're in the same room. Who is this person? Does anyone know? Actually, I'll ask someone if people can throw it in the chat. Anybody know who this person is? I would hope many of you would know, but maybe not. Rodney Brooks, yep. So this is Rodney Brooks, who's just had a pivotal influence on my career. And he's a professor emeritus at MIT. And Rod wrote a paper back in sort of 1985, 1986, aspects of mobile robot visual map making. That was one of the first key papers that I latched on as a grad student. So my dream was to build a robot that could navigate using the sort of geometry of the world, that could sort of, I'd worked, so a little bit more of my history. I grew up in Philadelphia, Northeast Philadelphia, and I was fortunate to get a General Motors scholarship in college, and I worked at the CPC Wilmington assembly plant in 1985 and 1986, 50 miles from my house, but on the way to Baltimore. If you ever drive up through Delaware, there used to be a really huge GM plant just off the highway. And I worked there 2 summers when they kind of rebuilt the plant to take in more robots. And they had to rip up the floor and put in a new special concrete floor with wires in it for the autonomous vehicles to follow wires in the floor. And I said in my grad school essays, that's crazy. The robot should be able to navigate the way people navigate. And so, but in this abstract of this paper, Rod sort of captured, mobile robots sense their environment and receive error-laden readings. They try to move a certain distance and direction and do so only approximately. Rather than try to engineer these problems away, it may be possible and may be necessary to develop map making and navigation algorithms which explicitly represent these uncertainties, but still provide robust performance. And to me, that's kind of like the guide star of my sort of navigation career. How do you represent uncertainty? This is kind of like but you want to, it's the balance between representing uncertainty, but still providing robustness and efficiency, and having a robot that you sort of turn loose in the world. It's a tremendously challenging problem, sort of a core problem. And one thing that Rod said in that paper, he talked about using a relational map that is rubbery and stretchy rather than a more rigid 2D or 3D coordinate frame. And Rod wrote, these problems are far from solved, and much remains to be done to produce complete solutions. Now, someone might say that, oh, SLAM is solved. Why are you still working on SLAM? You know, the confession, I'm still working on my PhD thesis 35 years later after I started. And I think a lot of it goes back to this question of representation. So Rod proposed sort of topological representations, kind of the first to point out the loop closing problem. And I want to go even further back in time. So not many people know that Rodney Brooks' roommate at Stanford as a grad student was a true pioneer, Hans Marvick, who used the Stanford cart, built the Stanford cart. And so I'm going to play a clip from 1996.
Back in the 1970s, Moravec started what he thought would be a very simple task. He hit a problem.
There were things that, although they at first looked like they might be easier because human beings do them more easily, that in fact turned out to be heartbreakingly difficult. And those were things like looking at the world and seeing what objects there were in front of the camera that was connected to the computer, and moving around competently in the world, you know, the typical robot tasks.
Each flash here represents 15 minutes of computing time.
So Rod did this experiment in Stanford in 1976 or 77. The processing was so limited today that he had to wait 15 minutes each time the robot moved to process the camera data. He used a linear slider with a single camera that he moved through 9 positions. He did some incredibly innovative things. He built his own wireless communications system, and he created a sort of this pyramidal stereo system. But to me, this notion of that, knowing where the objects are in the world, and this may not seem like why is this a problem in the era of deep learning, but knowing the position of objects in the world and the ability to kind of move around confidently and not bump to them, and to do things with them, maybe mobile manipulation, still tremendously hard to this day. Now, around the same time, in terms of that sweet spot of those core papers, there was some pioneering work in France, and I probably shouldn't play this one, but this is from French television in 1981. I've got a great historical collection of robot videos. Raja Shetila was a pioneer in trying to use more geometric, consistent world models with explicit representation of uncertainty. This is a robot called Hilaire in Toulouse, France. And Raja's approach was more about decoupling the motion planning and the localization and the problems, and trying to explicitly represent uncertainties and kind of stitch everything together. And this is, Rod Brooks kind of rebelled against this in creating some assumption architecture.
Alors voilà comment se présente.
I won't do this. This is a great video, but that's Raja talking about the problem in 1981. Some other early influential work came from Smith, Self, and Cheeseman. So the stochastic map for spatial relationships. And really, I say that if it wasn't for uncertainty, I wouldn't be in business. And I think that along the lines of what Rod suggested, rather than treat spatial uncertainty as some kind of side issue, it's really the central challenge. And how do we create sort of networks of spatial relationships and try to incrementally update them? And then an implicit there is, how do you represent those uncertainties? And implicitly here with the error ellipses that are being drawn is a Gaussian assumption, which I still think is a problem, and I'll come back to that time permitting. And so this basic problem of SLAM, simultaneous localization and mapping, is it's like pulling yourself up from your bootstraps. Or I wrote a paper once for IROS 1991 of simultaneous localization and mapping, which came first, the chicken or the egg? Because if you have a map, you can localize yourself relative to the map. And if you know your position, you can build a map. But how do you do that at the same time? And so, let's just say a robot has some position with some starting point. It makes observation of some objects. There are uncertainties in those observations. The robot moves. There's uncertainty in the motion. And then we want to re-observe the first 2 objects and now observe a third object. How can we combine and all those measurements have uncertainty. How do we combine the measurements together to come up with sort of the optimal estimate of the location of the objects in the world and the trajectory of the robot? And one of the big challenges, these are typically multimodal uncertainties. There is the data association problem of which measurements correspond with which features. So uncertainty representation is kind of a core issue. And in general, so what we try to do, so in my thesis, we did localization given a map or mapping given locations. And this is early sort of screen capture from, we had a French robot that we'd navigate around in the basement and using Kalman filtering and sort of a Gaussian representation of error to sort of predict measurements from landmarks or beacons, we called them, the features in the environment, and use that to correct. So here the triangle is the dead reckon position, which was drifting really far off course with this kind of wheelchair design robot that the wheels slipped really badly. But the goal was to have the robot build its own map ultimately. And we couldn't do that. It just wasn't possible at the time. The actual name of SLAM, Hugh and his students, Hugh Jordan-White was my advisor, a tremendous friend, just an incredible energy and enthusiasm. You know, in my thesis, I called it simultaneous mapping and localization, which would be SMALL if you made an acronym. And Hugh realized that SMALL is not a really good name for writing grant proposals. And if you switch the order of the L and M and you get SLAM, like Ken pointed out with the slam dunk, it's a more sort of powerful thing. And I love Hugh, but he had this attribute. I don't know if Greg Hager's on the call, but Greg was a lab mate of Hugh's at the GRASP lab, and Greg's work actually was very influential in my work too. Task-directed sensor fusion, ICRA 1989. And Greg explored non-Gaussian representations of error, which was truly before its time. I have a student now that is kind of trying to do the same thing. My student Chad, we're doing non-Gaussian inference for this, and it goes right back to Greg's thesis as one of the first to try this. But Hugh had this way of saying that a problem was solved when it wasn't really solved yet. And so, and I look back to all so here I want to sort of insert 20 to 30 years of kind of history and research about the SLAM problem. But this is Hugh and Raja, much older than in the video. And if anyone knows this person, Sebastian Thrun, just a key kind of person of the story. I'm sure many of you have the probabilistic robotics book on your bookshelf. For me, it's just out of my reach. And this is sort of arguing over different types of uncertainty representation. It's something called the 2002 SLAM Summer School. And folks like Henrik Christensen and Wolfram Burgard and Mike Montemirlo and just the Juan Domingo Tardos. And we kind of built this community of folks sort of roughly in the sort of 2000, 2002, 2004 timeframe, where a whole lot of people kind of rushed into the SLAM problem. And it was this sort of real tremendous enthusiasm and energy. Now, I'm sure if you weren't working on SLAM and robotics back 20 years ago, I bet some folks were probably a little bit annoyed that, hey, these people working on SLAM get to make all these cool videos and get a lot of research funding, but hey, there are a lot of other robotics problems as well. But to me, I think some of my dear colleagues who said SLAM is solved, and I can point you to saying it in 2002, saying it in 2004, et cetera. I think that it's more of, there's plenty more work to be done, and I want to try to tell you why. And to me, if we think about why mobile robot navigation and mapping is difficult, I like to sort of divide it along these different axes of problems. So one is representation. How do we represent the environment? So going back to what Rod Brooks said, and Raja Shatila and Hans Marvik, and how do we represent the world? It's sort of this fundamental question. And then how do we solve the inference problem? We have this ever-growing, as you map a larger environment, inference problem. And the uncertainties all become kind of correlated. And one of the early challenges was how do you map a large environment? How do you achieve efficiency? But it's not just enough to make a map that might look nice to a human. We want to build systems and make them autonomous. And that really comes from the underwater, the DARPA challenge type thinking. So we probably now had several hundred SLAM PhD theses. And I think they're kind of exploring this space of different types of representations, so metric versus topological, dense representations, things like Kinect fusion, and more recently the sort of NERFs. One of my students is looking at NeuroDescript at NDFs for trying to represent 3D objects and change detection. And we're moving more towards semantics, so how we represent the world in terms of objects and sort of more of an understanding more on human level terms. And there's this biological question. We have a collaboration with folks with BU on an ONR Murray looking at navigation in the animal brain, with grid cells and place cells and fMRI imaging of humans doing kind of maze tasks. And this whole question of how do you take a local egocentric view versus developing more allocentric, world-centered views. And then obviously there's a big state estimation problem under the hood. And the data association problem traditionally was one of the real hard parts about SLAM, because when you bring in the discrete uncertainty of different hypotheses, you turns to a multiple hypothesis tracking problem that blows up exponentially. And more recently, machine learning has become just a really important tool. And we're using learning in my group, and you could argue that the whole problem, just why don't you replace all this with just an end-to-end learning framework? And I could talk about that if there's time in the questions. But we want to couple perception to planning and control and close the loop on autonomy. And we want to go from demo to deployment. And what does it take to build systems that can sort of confidently navigate in the world? And so, so just a little bit about, so the kind of the quick summary, and I can point you to other places to look for more detailed how the sort of community evolved. So SLAM is this high dimensional nonlinear convex optimization problem. For example, if you're using laser scan matching, which I'll show you in a second, when you try to match two laser scans, you get this kind of rather unpleasant objective function for matching, which might have a well-defined peak, but might not have a well-defined peak. But the typical representation, and I credit, really Frank Dellert, Michael Case for championing factor graphs as a representation, where you have a sequence of robot poses, potentially some landmarks, and we could talk about SLAM with and without the landmarks, measurements of those, and then loop closing constraints, which is when you go back to a place you've been before, and enforce a kind of constraint. And there's this inherently sparse structure due to the fact that all the measurements are relative. And so how do we kind of exploit that? And so roughly from 2000 and onwards, there was a shift from what I would call more landmark-based representations to pose graphs. And so I'm going to show you an example from my former student I co-advised with Seth Teller, Ed Olson. This is in the Stata Center, and this movie has time as the vertical axis. So Ed is navigating his little robot around part of the building, collecting laser scans, and what the red lines that are drawn vertically are loop closure constraints, which is when the robot drives back to a place it's been before, and it's able to apply sort of an error correction. And so if you represent the entire pose history of the robot, it gives you a way to sort of solve for the poses and render back your perception data. Here's another example. This is the Killian Court data set that Michael Boss, Paul Newman and I took in 2001. This is one of the SLAM benchmarks, and this is in buildings 1, 3, 5, 7, 2, 4, 8, 6 in MIT. And so this robot's right now is along the MIT Infinite Corridor. Now it's up at building 9, 13. It's going to come back down building 5. If you know the campus, building 3, the Infinite Corridor again, building over near physics, where Jim Bellingham's home base, and then back. And if you watch closely right now, the algorithm applied the loop closure constraints. So until that point, it was just dead reckoning. But if you know back where you are and you can correct the errors, you can sort of correct the pose graph. And here from Ed's thesis is a little overlay of that trajectory that I just discussed overlaid on the MIT campus. There's the dome, the main dome. And so if you, and more formally, that you can pose this pose graph, state the pose graph optimization problem. And my former student, David Rosen, who's now at Northeastern, very kind of deep into the math of how you formulate pose graph optimization. And there's really some rich challenges here, because a lot of our work is sort of, there's a fingers crossed aspect that things tend to converge and when the measurement uncertainty is good. But how would you sort of certify SLAM solutions? And there's a whole math version of this talk, which I will not attempt to give now, but it relates to, David has made a lot of progress on developing certifiably correct solutions where the algorithm can kind of self-certify. And I think that leads towards trustworthiness. If the algorithm can basically be confident that it truly has made a good map. Now, let's see. So I realize I covered a lot of ground here. Let me just go back. I might show you one more example. So this is a video that I showed earlier, but this is my student Harther, who worked on underwater work, ship hull inspection, mine neutralization. This is Harther processing data from the PR2 robot on the second floor of the building, right where I'm sitting now. Actually, I'm just over here. And this is using stereo vision data from a Kinect that is being back projected into the world with this kind of this dense model, so you can sort of see the structure of the world. And if you see here, the robot's going down a corridor. When it comes back in a second, you're going to see two corridors, that the corridors kind of misaligned. But as the robot reobserves some world structure, like there was a dartboard here for many years, it's able to sort of snap the map into place, and you get a kind of map that looks nice. And this is the part of SLAM that is kind of solved, in the sense of using vision in a relatively static environment, not too big of a pose graph, and sort of building a rendering that you could use, say, for flying a drone or whatnot. But for the purposes of this talk and for my current research, despite the fact that we have visual maps that look nice, the robot's not really understanding the world. It's one thing to sort of render the 3D data and that we can say, oh, that looks like a chair, that looks like a table. But if we want a robot that can sort of interact, for example, with people, maybe helping an elderly person to age in place in their house, I believe we need some understanding of the world more in terms of objects. And I think that a more compact object representation can lend itself better to shared autonomy with people. It can be more sort of efficient and compact versus these sort of rich, dense 3D models, and it can be more robust and less brittle if the world changes. So let's see, maybe I should check the chat here and make sure everything's good. And if, let's see, so the history lesson is done. I'm gonna talk about my current research and my group of students here. So when I went on leave to Toyota, my group kind of went small, had some students like Sudeep Pillai, Dion Furi, who finished up. And but coming back from the Toyota leave, I've kind of rebuilt my research group. And there's this, so this is a picture from last week before I gave a talk here at MIT, a bunch of my students, and I'd love to tell you what each one is working on. Just a couple of things I'll point out is I had two Navy officers. So we're fortunate that we typically have Navy officers that rotate through MIT. And Jesse here just finished up his thesis. He's gone back to the fleet. Brendan is actually a Navy PhD candidate, and he was off at the wrestling championship, even though he's much older than most of the other wrestlers, just tremendously committed guy. And Jesse and Brendan are working on how we might have an autonomous underwater vehicle help a human scuba diver to navigate. And if there's time at the very end, I'm going to show you some of the results from Jesse's thesis in a recent paper we submitted. And of my various students, I'm just going to pick a kind of sampling of probably pick one or two projects to talk about just for time constraints. In addition, we've had UROPs, so Nicole was an MN, Sophia was a visiting high school student, and then a visitor from Cornell, and Amori is an MIT UROP undergrad. And we try to use like small terrestrial land robots as a kind of proxy, because underwater vehicles are so expensive, so easy to lose, all the comms and everything. And so we want to have a sort of hands-on capability in the lab where we can test algorithms. My student Alan here is in the joint program. Alan's from Louisville. He's working on cooperative navigation of multiple AUVs, trying to develop certifiable localization from range measurements, taking some of the sort of David Rosen math and applying it, actually looking at, say, like what Ryan Eustace did in his postdoc with Louis Wickham of cooperative localization with range measurements for underwater vehicles, and I had a student, Alexander Barr. We're trying to revisit that to try to have high integrity solutions that can self-certify. And the challenge is when you're using just range measurements, you have really non-Gaussian errors, and it's hard to sort of guarantee convergence and so forth. This picture is in the Building 31 motion capture facility with Aeroastro. Let's see. So, but the main focus of, say, on our work on the recent Office of Naval Research MURI grant with BU called Neuroautonomy is to try to do object-based navigation. And if you look in the biological literature, in say the brains of rats, there are different pathways for information flow that are more based on location and more based on objects. I believe that this question of like, where am I and what objects are around me are pretty fundamental. And how do you handle ambiguous situations? How do you have, and in fact, during COVID, when we couldn't get in the lab, I came up with a challenge for one of my new students who was stuck in his dorm is, these are a bad example, but could you navigate with playing cards as landmarks? And one of the things is that if a playing card has a flip ambiguity, and that may seem like not a big deal, but for a lot of our algorithms, when they work, they work. but when they don't work, they really don't work. There's this kind of chasm between like what typically works and what typically doesn't. And kind of a part of the Rodney Brooks playbook would be to look at the assumptions that you're making and what happens when you violate those assumptions. And so we had a paper in IROS last year looking at how you tolerate flip ambiguities in objects, or and in general, any sort of ambiguity about an object location or the orientation of a symmetric object, it gives rise to multimodal uncertainties, and these can sort of break the estimators. And so, so let's see. So I'm just going to give you a few examples. And so my student Kevin Doherty is the most senior student in the group. He's in his 5th year, and he's in the joint program and is motivated by robust long-term underwater mapping. He did a lot of really impactful, interesting work with Yogesh Girdhar at Woods Hole and on sort of sampling in the ocean. And obviously with no GPS, we don't have Velodyne LiDAR scanners. We have very limited communications. Probably a sparse environment where maybe things are going to move over time, and a high cost of failure if you're going to lose your vehicle. What we'd like to do is to how do we robustly navigate based on a more object-based representation. And so what we're kind of been doing the last year or two, and this is a very old slide. This might be one of the first PowerPoint slides that either myself or Paul Newman made back in when we started using PowerPoint in like 1999, is this sort of back to basics and think about the uncertainties that accrue when a robot moves and takes uncertain observations of the world. And really, like Greg Hager's thesis, the big thing is it's non-Gaussian. We have these different modes of uncertainty, and there are different ways of structuring this problem, but how do we find the most likely set of robot poses and landmarks, X and L, given the measurements Z? And we're going back to basics, but informed by new tools. And so machine learning has led to these remarkable advances in computer vision and object detection and so forth. And so this works a couple of years ago from ICRA 2020, looking at using mixture models to try to perform robust semantic slams. So this is one of the papers Kevin was the leader on. And how you can pose the problem where you have not just the locations of the robot and locations of the landmarks, but the actual semantic class of the objects. What if we have different types of objects? And just to give you a flavor of this, for any PhD student, I encourage you to have like a thesis statement of your thesis. Like, what's the central question? And Kevin's thesis of his thesis is, how can we develop systems that can operate long-term, learning and maintaining an economical semantic representation of the environment, backed by the robustness and mathematical rigor that we've come to expect of autonomous systems. So we're trying to like pull in some of the David Rosen certifiable kind of way of thinking, and also, but try to think about this more semantic problem where we have discrete and continuous uncertainty. So so just a little bit, and I'm a big student of the community, and I almost like, I have just so much admiration and respect for my colleagues like Andrew Davis and Frank Deller, Nikolai Atanesov at CSD, Luca Carlone at MIT. There's a lot of really good work out there, and there's this sort of community, and but a lot of in terms of bringing semantics into navigation, we think there still is some good work to be done. And if I look at in particular, multi-hypothesis methods and trying to do robust SLAM. So folks like, Nico Sunderhoff has been a pioneer for robust methods, and like these pose graph optimization techniques, if you insert some mistakes into the pose graph, all bets are off, things go wrong. If you want to try to explicitly enumerate all the potential hypotheses, you lead to this sort of computational explosion of my multi-hypothesis tracking. And Michael Case has a really good recent work that kind of navigates this well with MHISAM2. In our own group, this is going back to the 2020 work, the mixture models is sort of an assumption, so it's an approximation for robust semantic SLAM that can avoid some of the exponential complexity of the multi-hypothesis methods. And effectively, we're setting up factor graphs now where there's a discrete decision variable, which might be about the data association of a measurement or the class of a type of object. And just to give you a little flavor of this, this is and part of me is like almost like embarrassed or ashamed. Like, we're using April tags, which Ed Olson, our former student, invented, QR code type things as a way to do experiments where we can try to isolate different phenomena. And in some ways, it's almost like going backwards. Like with LiDAR scanners and even sonars, we could do pretty good demos in the cartridge of MIT 20 years ago. But now we want to try to understand the world more in terms of objects, and it's surprisingly hard. And so actually, I'll play this video here. So this is so using these little MIT race car robots that Sertaç Karaman developed for MIT teaching with a LiDAR scanner, we basically had and a camera. Sorry, so we're not really using the LiDAR, using the camera to sprinkle the world with some April tags where the IDs, whether they're odd or even, define two different classes, and then sprinkle in a misclassification rate and add some extra odometry error to make it harder. And here's, so going around buildings 1, 3, 5, 7 in MIT, Meki, Ocean, and comparing if you know the ID of the tags, and that's on the upper left here, versus using a maximum likelihood formulation that's just going to pick the most likely mode, and then versus having a semantics aware and different flavors of max mixtures. And the NH here stands for null hypothesis. And the important take home here is that even for this what might seem like a relatively simple scenario, the max likelihood solution is not able to close the loop when the robot comes around. And if we run it kind of further, you can see that so what we want to strive towards is getting the same kind of solution as the known data association without being able to handle some of those ambiguities. So this work's a couple years old now, pre-COVID. Whole lab kind of shut down like everyone else's. And Kevin also has some results for the Kitty data set, but I think I'm going to stop that and then go. I mentioned the playing card things. This is an IROS paper. Actually, this appeared in the fall. And I won't talk about that one for time, but this is the work of Zichi, along with Chad and Kevin. But I'm going to talk about, so our lab, we're actually kind of tired if I'm a little out of breath. We submitted 8 papers to IROS and RAL deadlines about 2 weeks ago, or a little more, beginning of the month. And I'm just going to pick one to talk about. And so if you think about, SLAM can provide a location queue to help supervise an object pose estimation system. And so what we want to do is do understanding the world in terms of the objects. These are some YCB objects: Spam, Can, Cheez-It Box, Sugar Box. And the essence of the idea is to try to take a sort of baseline detector, like say, and we're using a detector called DOPE that Dieter Fox developed. It's pretty state-of-the-art. And working on how we can have a robot can automatically generate pseudo labels for new data that it's acquiring using its pose estimates as a sort of as a self-supervising queue, and then improve the pose detection performance. And so here's an example of a DOPE detector applied to some of the YCB objects and the YCB videos. And despite all the progress in deep learning, and I'm sure 3D pose estimation for objects is still really hard to do. So Zichi's been working on sort of pre-trained training DOPE detectors to try to estimate the object locations. And my dream is that, like, objects, any old objects could be just as if they were an April tag, just a sort of a geometric reference. It's surprisingly hard. And so so what we're doing is basically taking the sort of, this is a pre-trained detector, some pose predictions from, I think, using This is using OrbSlam, and then solving an optimization problem also with some automatic covariance tuning to get the uncertainty. So the location cues can help you basically figure out what your uncertainty should be on your detector. And the kind of before and after is, this is the sort of before detector, and you can see the various kind of outliers and problems it's having. And this is the after detector. So what we're getting is much more stable estimates for the YCB objects, like the Cheez-It Box and the object poses. And so I have a results video here, and the important thing here to see is, so there's sort of, it's doing this kind of pseudo labeling and fine tuning of how it's working. Let me show you this video, and then I'm going to wrap up. So this shows the left is kind of without our technique, and the right is with our technique. And what you should see is that by using this sort of automatically pseudo-labeled data that the robot's acquiring from moving over multiple positions, it's able to train a much better pose detector and then do much better estimates. So the YCB video sequences are really short. They're frustratingly short. We need more data for object-based SLAM. In fact, one of the key things we're going to do in the next few weeks is take bigger data sets and make them public. This is just obviously like very simple scenario, single robot with a camera driving around an object on the ground with some April tags to sort of ground truth the object pose. But what you're seeing here, if you compare left versus right, is you're seeing much more stable estimates of the robot poses. Why is that important? Well, for a lot of machine learning algorithms, people think about getting like 67 versus 68 versus 69 versus 71% in mean average precision. But if you want to have a robot navigating the world, we need more reliable estimates. We need algorithms we can trust. And so let's see, there was one more video I was meant to play there, but and so we have, let me see if I can show you this one. No, okay, this one. So here, if you compare just the video on the right here shows the kind of the red versus the blue. Effectively, what you're getting is that with the self-trained detector, the robot, and then when we use that for navigation, we get much better pose estimates. So it's effectively we're doing, we want to be able to, on the fly, learn about objects and be able to use our navigation to better recognize them and then better recognize the objects to better navigate. So we're still dealing with very kind of simple scenarios. So we have a recent IROS paper, just hit IROS on this. And let's see. So I want to sort of wrap up now. It's 11:54. So what would I say sort of the open challenges? To me, long-term autonomy in highly dynamic environments has been elusive. And I think much work remains to create truly sort of trustworthy autonomous systems. And I want to create robots that get better with time, not get worse with time. A lot of robots, you're driving around once, you make a map, it's like, cool, we solved the problem. You drive around 10 times, the map gets worse because little errors accrue. And in fact, the pose graph representation hides a lot of sins. It's really, what I want to do is develop robots that can make models that are isomorphic to the world, that really match, where there's one wall in the map, where there's one wall in the world. And then I also believe in shared autonomy, that we want to basically enable robots that can improve their interactions with humans and other robots. And I think the semantic representations can lead us to systems that have that character. So let's see. So let me just check here. And I should probably take some questions. So, so I have a bunch more stuff I'd love to show if I had time, but maybe I should stop there and take questions.
John, thank you so much for that beautiful talk. You've brought us from the foundations of SLAM to the current challenges. And clearly, being able to trust autonomy is at the top of our list too. So we look forward to continuing to work on this in collaboration with you and your students. Such wonderful work. We have some questions, I believe, in the Q&A, which I'll get to in a second. First of all, I wanted to open it up to any of the panelists who'd like to ask a question. Tony, I think you have one.
Yes. Hi, John. Thank you for the great talk. A couple of questions. First of all, are you using multiple modalities of technology, for sensing in your work? It wasn't clear and how do you feel about that? I know there are different schools of thought. Right.
Yeah, I think when I talk about multiple modes, there's like multiple sensing modes or multiple modes of uncertainty for a particular sensor. And I was primarily motivated by the latter, but in fact, we do use many types of sensors. And so, for example, we work on visual inertial fusion. We work with underwater sonars. I've done work kind of fusing LiDAR and vision. And I think that the problem of multi-sensor fusion is a hugely important problem, and that's an important theme.
The second question is, what's your assessment of the state of being able to discern hard objects versus so-called squishy objects, like
that's a great question. Yeah,
an empty plastic bag versus a boulder?
Yeah, I think that those are really hard problems, and we have this amazing generation of young faculty that are coming along. For example, I think of David Held at Carnegie Mellon, my colleague Alberto Rodriguez in MIT MECI, looking at using tactile sensing trying to manipulate cloth, manipulate soft objects. From my perspective, we need to find a way to get kind of these sort of physics-based models of the world. And I think that I want to use the robot as the experimenter. Like imagine a robot that could do sort of experiments in a room over the weekend with no one around, and it could try to effectively acquire its own data to figure out exactly what you just said, which objects are squishy, which ones are hard. Now that it might break the objects, or it might be you need to clean up a really big mess on Monday morning when you arrive at the lab. But I think that those are great questions. I don't know the answer per se, but I'm more of a fan of more explicit representations where we explicitly represent the physics and the structure. I'm a little nervous about the kind of black box techniques where it's just data in, data out, and we don't really understand what's happening inside the black box.
And of course, you have a different challenge when you're you have a self-driving car going down the road at 50 miles an hour, and there's an object. Is it an empty paper bag, or is it something that I need to?
Yeah, those are hard questions. And I think, and there's the whole question of simulation. Can you create simulations that you could trust and try things in simulation? The whole question of how to manipulate, represent compliance in objects. Like my colleague Russ Tedrick has championed a simulation framework called Drake and work to try to better represent things like contact. There's things like Mijoko. These are really rich, important areas. I don't know the answers.
Thank you. So other panelists, we have one more panelist question, and then I'll open it up to Q&A.
I don't have any questions. Great talk, by the way, John.
Thank you so much.
Kara?
Yeah, this was great. Let's go to the Q&A before we come back to panelists.
Okay, so there's one in the Q&A. It's does interacting with unpredictable moving objects, such as a human being, fall under the scope of SLAM? Could you share your thoughts in robotics on the challenge of interpreting human behavior? Those both are
They're both great questions. Both great questions, and I think that if you early days in robotics, you would sort of screen out the moving objects. So if you could just look over time for temporal consistency and take out a sort of person walking down the corridor. But in general, one of the things that's hard to deal with is long-term changes. Like if, say, a piece of furniture gets moved, or it's not so much the sort of highly dynamic things can be screened out, but the longer-term, more what we might call a semi-static environment, those can be very challenging. And I think that interpreting human behavior is a hugely important problem. In fact, it's a big focus, a part of the group I'm involved with at Toyota Research Institute, trying to do things like predicting, is that pedestrian going across the road? Predict the actions of another driver. And I think ultimately the interpreting human behavior comes into it in autonomous robots, how you could sort of navigate safely amongst people. I tend not to focus on those too much myself. But maybe even with the diver AUV project we're trying to do, that we might try to get into, like, can you recognize if a scuba diver is having difficulty by the way that they're swimming or behaving, for example?
Okay, very good. It's one of our IAA initial seedling projects was about representing groups of people walking, and does the robot detect whether it can go through the group or should go around the group based on social behaviors. One more question in Q&A, and then we'll wrap up. Maybe I missed this in the presentation. Would you be able to talk more about or point to some of your work trying to really move away from Gaussian assumptions that are prevalent in SLAM?
Yeah, that's an excellent question. I just didn't talk about it for time, but I have a wonderful student, Chad Huang, who seems to always be in the lab no matter when I come. And we have a paper called Normalizing Flow, Incremental Smoothing and Mapping is one example where we're using normalizing flows to represent non-Gaussian distributions in a sort of ISAM framework. We have another paper we just submitted that tries to do this in the context of, well, let me go a little side story. So these very high dimensional state estimation problems with non-Gaussian variables, there's a whole conversation about sampling techniques and different ways of doing that and trying to be efficient. What we've actually discovered is that, of all places, in the astronomy literature, there are folks that have developed some really amazing, efficient, high-dimensional state estimation packages. And so we're using one of those and adapting it for the sort of SLAM application, accounting for the sparsity. So if you want to send me an email, I can send you a link to a couple of papers we have in archive. I just didn't have time to talk about it today, but ultimately it all kind of fits together in my head. It's just a little fuzzy.
That's great, John. We're out of time. We really appreciate your thoughts today. An excellent talk. I've just put into chat the link to your marine robotics website for people to get more information. And we look forward to working with you in the future. Thank you so much.
Thanks, everyone.